In this video, we are going to discuss the effect of electronegative atoms in the diastereoselectivity of nucleophilic addition to carbonyl compounds, and we'll discuss with this particular molecule where there is a carbonyl group and it is attached with a asymmetric carbon which is substituted with a electronegative group. Now this electronegative group can be O-alkyl, N-alkyl, thioalkyl, etc. But the condition is that it is not a living group. Now when the nucleophile will attack the carbonyl carbon, then it may approach from both the faces. We know that carbonyl is a planar group and it has two faces and we designate them as Re and Si. Now in this case here we have to give oxygen as first priority atom, right? Then this will be second, this is the third one, and this is clockwise direction. Therefore the upper face which is towards us is the Re face and the lower face will be the Si face. Now if the nucleophile approach from the Re face, then we can get this particular isomer, stereoisomer, and if it approach from the Si face, then we can get this particular stereoisomer. And A and B, these stereoisomers, their relationship is diastereoisomer. Now, one of the diastereomer will form as a major compound. It is always experimentally observed, which we term as diastereoselectivity. Now, to know about the major isomer, we have to use the Falkinen model. Now this is the Newman projection for this particular molecule. When there is a electronegative atom, electronegative substituent is present in the asymmetric carbon, then in the Falkinen model, this electronegative atom should be placed in the perpendicular to the carbonyl group. Then phenyl will take place of the medium size group and hydrogen will take place of the smallest size group. The nucleophile will attack as usual from this direction. We know that this particular angle, this is 107 degree. This is called Barji-Danich angle. This is 107 degree. This is called Barji-Danich angle. And after the attack, we'll get this particular conformation. This is a staggered conformation, therefore this is stable. And what we have observed that this phenyl and methyl, they are in the same plane, and hydroxy and X, they are in the same size. If X is if it is above the plane, then OH will also be in the same plane. That means their relationship is cis, right? Now the product will be B. That means since in the original molecule X was above the plane, therefore it will also be in the above the plane, and OH and X relationship will be cis. That means B will be the major diastereomer. Now the question is, why this electronegative atom or electronegative group is perpendicular to this carbonyl? It is because the sigma star of CX bond, right, and pi star of this pi bond, they can overlap, and that will result lowering of energy of lowest unoccupied molecular orbital, and that will actually help the nucleophile to attack the carbonyl carbon. Thank you. In this video, we will discuss reversal of stereoselectivity by chelation. For this discussion, we have selected this molecule where this is a carbonyl group. Carbonyl group is attached with a asymmetric carbon, and asymmetric carbon is attached with a electronegative group where the atom sulfur is having lone pair. Now when it is treated with sodium borohydride, then it is observed that this is the product. Same molecule, when it is treated with zinc borohydride, then the major product is this one. That means sodium borohydride will give this as a major one, and zinc borohydride will give this as a major one. And what it is observed that simply there is a reversal of stereochemistry of the newly generated asymmetric center. Now, in presence of metal commonly involved in chelation, then sense the stereoselectivity. Now, what is chelation? Chelation is nothing but when a metal can bring 2 or 3 heteroatoms near to each other by coordination by a lone pair. That particular phenomena is called chelation. Now, what are the metals commonly involved in chelation? They are nothing but magnesium ion, zinc ion, copper ion, titanium ion, cerium ion, magnesium ion. Lithium, it can undergo chelation, but sodium and potassium, they never will undergo chelation. Now let us consider the reaction with sodium borohydride. For that, we'll arrange the molecule in Falkenhayn model. Since S-methyl is the electronegative group, therefore it will be perpendicular to the carbonyl. Ethyl will be the medium-sized group, hydrogen is the smallest group. The nucleophile hydride will attack from the smallest group, and as a result, we will get this molecule. This is the staggered conformation, the most stable conformation. And here we have observed that ethyl and phenyl, they are in the same plane, and OH and SME, they are in the same side. That means their relationship is cis. And since S-methyl is above the plane, OH will also be above the plane, and their relationship is cis. Now, in case of zinc borohydride, the representation in Falkenhayn model is same, but here, since zinc is present, what the zinc 2+ ion will do, it will bring both oxygen and S-methyl group near to each other, so that this lone pair of sulfur and lone pair of oxygen can coordinate with zinc 2+. This is chelation. This phenomena is called chelation. Since S-methyl is going there, therefore this hydrogen will go there and ethyl will come here, and this time the hydride from borohydride will approach from this side and will get this molecule, this particular conformation of the molecule. Here ethyl and phenyl, they are not in the same plane. We have to bring them to the same plane. Phenyl will come here, hydrogen will go there, and OH will come here. And here what we have observed, that S-methyl and OH, their relationship is trans. If S-methyl is above the plane, then OH must be below the plane. Yes, this will be the configuration of the molecule. And if we compare between A and B, simply there is a reversal of configuration of this newly generated asymmetric center. Then A and B are diastereoselectivity, and we can conclude that chelation has reversed the stereoselectivity.